The process begins with receiving detailed measurements from an engineer. These measurements include allowances for machining, shrinkage, and material contraction during the casting process. Once the specifications are reviewed, a full-sized layout of the propeller pattern is created. The next step involves dividing the layout into sections at specific intervals. These sections are referred to as slices or cants. Preparing the cants is a process, as they will be glued together later to form the shape of the propeller blades. Marine propellers play a crucial role in ship propulsion, and their precision in design and manufacturing is essential for optimal performance. A hole is drilled at the center of the hub, which acts as a critical reference point for taking measurements. The foundry also utilizes this hole for setting up the pattern during casting. The prepared cants are carefully glued together, ensuring they pivot around the central hub. The pitch of the blade determines the precise offset required during this process. Once the cants are securely positioned, the rough steps of the blade surface are gradually taken down to create a smooth and contoured blade face. Simultaneously, work begins on the forward and aft sections of the hub. The forward end of the hub is secured only after ensuring it is perfectly perpendicular to the center hole. This ensures accuracy, as this face will serve as a reference point throughout the shaping process. Additional holes are drilled to act as reference points for further measurements. Once the initial shaping is completed, dowels are cut and positioned at various points to establish the required blade thickness. These dowels act as precise guides for material removal from the back of the blade, ensuring uniform thickness and accuracy. With the blade shaped, attention turns to the hub. The aft end of the hub is added and the structure is filled in to achieve the final form. In this case, the hub is shaped into a barrel form, which is a common design for marine propellers. To achieve a seamless transition between the blade and the hub, body filler is applied to create a smooth fillet. This ensures structural integrity and enhances the aerodynamics of the propeller. Once the fillet is shaped and smoothed, the entire pattern undergoes multiple coats of specialized pattern coating. This coating contains additives that prevent foundry sand from adhering to the surface, making the casting process more efficient. After all finishing touches are applied, the completed propeller pattern undergoes a thorough inspection to ensure all measurements align with the engineer's specifications. Once approved, the pattern is carefully packed and prepared for shipment to the foundry, where it will be used to mold and cast the final stainless steel propeller. Azipod propulsion is a revolutionary gearless steerable propulsion system developed by AB, in which the electric drive motor is housed within a pod outside the ship's hull. The assembly begins with outfitting the main Azipod casing. The casing, made from high-strength steel, is carefully fabricated and welded to house the electric motor and other critical components. Internal wiring, cooling systems, lubrication channels, and auxiliary systems are installed to prepare the unit for further assembly. Precision and quality control are essential during this phase to ensure seamless integration with subsequent components. The shaft line connects the electric motor inside the pod to the propeller. Thrust bearings are crucial for transmitting the thrust generated by the propeller to the ship's hull. These bearings are assembled and mounted with extreme precision to handle axial forces efficiently while minimizing friction. The installation process includes lubrication and rigorous quality inspections to ensure optimal performance under various operational loads. The electric motor's rotor, the core of the Azipod system, is installed next. This step requires careful alignment, as the rotor interacts with the stator to generate the necessary torque for propulsion. The rotor is positioned inside the casing and tested for proper clearance and balance. AB engineers conduct extensive inspections to confirm that electrical and mechanical tolerances are met. Before the Azipod unit is shipped for installation on a vessel, it undergoes rigorous testing. This includes functional tests, load tests, and simulations to ensure the unit meets performance expectations. AB engineers check for electrical integrity, rotational efficiency, and response to various operational scenarios. Only after passing these stringent tests is the Azipod unit cleared for delivery. Boat propellers in Mallorca, whether made of stainless steel, aluminum, or bronze, are subject to wear and damage due to continuous exposure to water, debris, and occasional impacts. Proper repair and maintenance are crucial to ensure optimal performance and fuel efficiency. The repair process begins with measuring the slope, which determines the exact pitch and alignment of the propeller blades. Any discrepancies can cause imbalance and inefficiency. The next step is to judge the extent of the damage, whether the blades are bent, cracked, or eroded, before proceeding with the appropriate repair techniques. For damaged blades, welding is used to restore missing or cracked sections, particularly for stainless steel and bronze propellers. Aluminum propellers often require specialized welding techniques to maintain their structural integrity. Once the welding process is complete, the propeller is balanced to ensure smooth operation and prevent vibrations that could damage the engine and shaft. After balancing, the blades go through sanding to remove imperfections and smooth out any rough edges. This step is essential for reducing drag and improving hydrodynamics. Finally, the propeller undergoes polishing, which not only enhances its appearance, but also reduces friction in the water, further improving efficiency. The first step is selecting the appropriate propeller blade template. Pattern making is a crucial step in propeller manufacturing, ensuring the mold accurately replicates the desired shape. First, sand is mixed with binding agents to create a sturdy mold. The bottom half of the mold is formed, followed by the upper half using sand molding techniques. Small holes are poked to allow carbon dioxide (CO) pumping, which hardens the sand. Once both halves are solidified, they are carefully aligned and joined to form a complete casting mold for the molten metal. Carbon dioxide (CO) is pumped into the sand mold through pre-made holes, reacting with a sodium silicate binder. This chemical reaction hardens the sand quickly, creating a strong, durable mold for casting. Completion of the bottom half. The upper half of the mold is created by packing sand around the pattern, ensuring precise shaping before hardening with carbon dioxide. Poking holes for carbon dioxide pumping. CO reacts with sodium silicate, solidifying the sand mold instantly. Molten metal is carefully poured into the sand mold through a designated opening. The metal flows into the cavity, filling every detail of the mold. It is then left to cool and solidify. The molten metal solidifies gradually, ensuring structural strength overnight. The manufacturing process begins with an in-depth design phase. Engineers analyze the specific requirements of the vessel, including its size, weight, speed, and intended use. Once the design is finalized, the production process moves to casting. The selected metal alloy is melted at high temperatures and poured into molds designed to create the propeller shape. The casting process must be precise to avoid defects that could affect balance and efficiency. After cooling, the propeller undergoes machining and finishing. Advanced CNC computer numerical control machines trim and polish the blades to achieve the exact dimensions required. This step ensures smooth surfaces and optimal hydrodynamic performance. The manufacture of marine propellers is a highly specialized process that requires precision engineering, advanced materials, and extensive testing to ensure optimal performance. Italian Propellers, a leader in this field, has over 35 years of experience in designing and producing high-quality propellers for various marine applications. In addition to standard designs, Italian Propellers offers custom-made propellers tailored to customer specifications. These can be based on existing blueprints or developed entirely in-house using expertise in hydrodynamics and navigation testing. The choice of materials is crucial for durability, performance, and resistance to corrosion. Italian Propellers manufactures propellers using two primary alloys: OT-Man alloy, brass and manganese, known for its excellent strength and corrosion resistance, suitable for pleasure boats and fishing vessels. Nibral alloy, nickel, bronze, and aluminum, offers superior durability and efficiency, making it ideal for high-performance applications such as speedboats, tugboats, and medium-tonnage ships. Caterpillar employs advanced, high-precision machining techniques to ensure each component of the Mach marine engine meets exacting standards for performance and durability. Rod boring and testing involve carefully drilling and refining engine rods to ensure a perfect fit. Much like tuning a musical instrument for flawless sound, precision in this process guarantees optimal engine performance. Plasma valve machining uses high-energy plasma to precisely shape and cut valve components. This advanced technique ensures extreme accuracy and smooth surfaces, improving the durability and performance of marine engines. It enhances the valve's sealing capability, ensuring optimal engine efficiency. Machining of cylinder heads is a critical process in manufacturing marine engines, requiring precision to ensure proper engine function and longevity. At Caterpillar's facility, this process involves cutting, grinding, and milling the cylinder head to exact specifications. The heads must be perfectly flat to allow for a tight seal between the engine block and the cylinder, ensuring maximum compression and efficiency. Special attention is given to the intake and exhaust ports, valve seats, and the overall surface finish. High-precision equipment and advanced techniques guarantee that the cylinder heads are capable of withstanding the intense pressure and heat generated during engine operation. Final component installation is a crucial stage in assembling Mach marine engines, where all major engine parts are meticulously fitted together to create a fully functional unit. This process involves installing components like pistons, crankshafts, valve assemblies, and turbochargers. Each part must be precisely aligned and securely fastened to ensure smooth operation and long-term reliability. The team follows strict protocols to ensure proper torque settings and clearances, preventing mechanical failure. Quality checks are performed throughout, and components are double-checked for any defects. This ensures that once assembled, the engine will perform optimally and meet Caterpillar's rigorous performance standards. Caterpillar's research and development, R&D, focuses on innovating marine engine technology, optimizing performance, fuel efficiency, and emissions. Engineers work on advanced materials, designs, and testing to continually enhance engine reliability and sustainability. On-site testing of every Mach marine engine is conducted to ensure flawless performance under real-world conditions. Each engine undergoes rigorous testing for power output, fuel consumption, emissions, and operational reliability. These tests simulate actual marine environments to validate the engine's efficiency, durability, and safety before delivery to customers. The manufacturing process of a Kaplan turbine involves several stages, each focused on ensuring high precision, durability, and performance. Kaplan turbines are primarily used in small hydropower plants and are designed to operate efficiently in situations with a low water head but a high flow rate. The first step in the manufacturing process is the design phase. Kaplan turbines must be tailored to meet the specific requirements of each project, considering factors such as water flow rate, waterhead, and power output. Global Hydro Energy, an Austrian company, uses state-of-the-art 3D CAD systems to design turbines. Engineers work closely with customers to understand their unique needs, ensuring that the turbine's design optimally matches the project's conditions. Additionally, dynamic flow simulations are used to model and optimize the turbine hydraulics. This helps in achieving the best performance possible by improving efficiency and reducing losses. Once the design is finalized, the next step involves selecting materials for the turbine components. Kaplan turbine blades, which experience high stresses and corrosive conditions, are made from corrosion-resistant and durable materials. High-quality steel or cast iron is commonly used for the turbine's hub, while the blades require even more robust materials. Before production begins, the materials undergo rigorous quality checks to ensure that there are no flaws, such as cracks or impurities. This is critical, as any material defects could compromise the turbine's performance and longevity. The next phase involves machining the turbine blades. Using advanced CAD/CAM systems, the milling process is precisely programmed and simulated before being transferred to the machining center. Depending on the size of the turbine and the materials used, the milling process can take up to 60 hours per blade. The blades are milled to achieve the exact shape and dimensions needed for optimal water flow and efficiency. Precision is essential in this step to ensure that each blade can perform as designed, as any discrepancies could affect the turbine's performance. After milling, the turbine blades undergo a polishing process. Skilled workers hand polish each blade to ensure a smooth and flawless surface. This is a delicate process, as the surface quality directly impacts the turbine's performance and efficiency. Once polished, the blades are tested for surface integrity. This involves using two-color dye penetration testing, a method that highlights any cracks or pores in the surface. This step, conducted according to strict ISO standards, ensures that the blades meet the required quality and durability standards. After the blades are manufactured and tested, they are ready for assembly. All core components of the turbine are assembled with a high level of precision to ensure that the turbine functions as intended. This includes aligning the blades to the hub and other components. 3D measurements are taken during assembly to guarantee the correct alignment and fit of each part. The assembly process is meticulous, with a focus on achieving the highest levels of accuracy and reliability. Once the turbine is fully assembled, it undergoes a series of in-house tests. These tests are critical to identify any potential sources of error or malfunction before the turbine is shipped to the customer. The turbines are tested for performance, ensuring that they meet the specified tolerances and deliver the expected output. Underwater propeller polishing is a crucial maintenance procedure performed on the propellers of ships and vessels. This process involves cleaning and smoothing the surface of the propeller while it is still submerged underwater, without needing to dry dock the vessel. The primary objective of underwater propeller polishing is to improve the propeller's efficiency and performance by reducing friction and fouling caused by marine growth and debris. Over time, a propeller can accumulate various contaminants including barnacles, algae, and corrosion, which can lead to a rough surface. These imperfections cause increased drag, reduced fuel efficiency, and less effective propulsion. By polishing the propeller, the surface becomes smoother, allowing for better water flow, which leads to increased fuel efficiency, reduced emissions, and overall better performance of the vessel. Underwater propeller polishing is typically done using specialized tools such as polishing pads, grinders, or high-pressure water jets, operated by divers or remotely operated vehicles, ROVs. The polishing process can be done quickly and efficiently, minimizing downtime for the vessel. This makes it a cost-effective solution compared to traditional dry docking methods, where the vessel must be out of service for an extended period. The benefits of underwater propeller polishing extend beyond just fuel efficiency. It also helps prevent corrosion and minimizes the potential for cavitation, a phenomenon that can cause damage to the propeller's surface. Regular polishing can extend the lifespan of the propeller and improve the overall lifespan of the vessel. In commercial shipping and the maritime industry, these advantages can translate to significant cost savings, making underwater propeller polishing a valuable maintenance practice for maintaining operational efficiency and reducing operational costs.